All right, so today we are very happy to have Gautam Satish Chandran here from virtually from the University of Chicago to tell us about the infrared divergences, memory, and asymptotic states in quantum gravity. Gautam, please.
Okay, well, thank you for having me. I would have liked to have visited UCSB at some point, but maybe now is not the best time. So I'll be discussing I'll be revisiting an old topic or problem in quantum field theory, and we'll see also in quantum gravity, in particular, these infrared divergences that one gets. And we'll basically be reformulating this problem in a kind of more geometric way. The eye towards is really trying to understand what are the space of asymptotic states, well, in quantum field theory, but in particular in quantum gravity. Okay, so this is some work it's part of my thesis work I've been doing with Bob Wald at the University of Chicago, and some of the preliminary ideas that I'll be discussing about can be found in this paper that I've highlighted here. This paper looked at memory effects, symmetries, and the infrared divergences in all space-time dimensions, including 4. So in this talk, I'll only be discussing memory in 4 space-time dimensions. And this is not the Midwest relativity meeting, let me just say. Okay, so just to give a bit of background, or why is this problem a problem, and why is it an interesting problem? Well, these infrared divergences that we'll be describing basically throughout this talk is the outstate of some quantum field are a ubiquitous feature, in the sense that if you do some generic scattering process, as we'll see, you'll generate these infrared divergences of the outstate. And so this has been known, for some time, well, basically well understood since the 30s. And it was in this very nice monograph by Abhay Ashtekar argued to, persist in the theory in any formulation of quantum gravity. So later in this talk, basically, we'll make these links between memory and, well, the physical consequence or physical observable of memory, which is, physical observable, which is these IR divergences, as well as these links towards asymptotic symmetry. So we'll make these connections more precise. And there have been various approaches to dealing with these divergences. Well, one is to do these inclusive cross sections, such as Bloch and Nordsik, and also pioneered by Weinberg, and only look at these IR-finite observables. So these, cross sections that one computes in the LHC. But it was really pointed out very nicely by Faddeev Kulish, and is currently active work to this day of, well, what if you really wanted to talk about the S matrix as a actual, operator between Hilbert spaces, and you wanted to actually construct an infrared finite S matrix? You would really need to include states, basically, which have these infrared divergences. And later in this talk, well, basically, this is kind of the one of the main punchlines of this talk, is that we derive these kind of general constraints on any Hilbert space construction of asymptotic states, which admit, well, these an infrared finite S matrix, which basically means that they admit these states with infrared divergences. Okay, so in QED, I should say, it's really generally understood that what one must do is kind of dress these asymptotic fields with so-called soft quanta. So this, I don't think Dirac mentioned the word soft quanta, but this is kind of an idea that was started around the 50s and was really pushed forward significantly, well, by Faddeev and Kulish, which is known as these Faddeev and Kulish dressings. And these were actually rigorously shown to, be preserved, these dressings preserved under scattering, due to in non-relativistic QED by Froelich. So I'll basically be mentioning, what these dressings are. We'll see the geometric origin of these dressings, and the reasons for why in quantum gravity, in non-perturbative, in any non-perturbative formulation of quantum gravity, these Faddeev and Kulish type dressings are really not applicable. Okay, and then finally, if the goal of an infrared finite S matrix is not good enough for you, the infrared structure of the theory, basically these asymptotic states, have been argued to play a significant role in, well, the decoherence and the entanglement effects that one gets due to soft radiation, basically. And so it was pointed out by, well, very nicely by these papers that there's quite a bit of information stored in this soft radiation, and really how to precisely talk about this soft radiation is really a statement of what this Hilbert space structure is. So, and finally, I'll mention that there have been various holographic proposals for asymptotically flat spacetimes. I'm citing some particular ones here. Well, Strominger has been really actively pursuing something like this, and I'll make some comments at the end of what the implications of our results are for the ideas that he's been putting forth. And there's also been these algebraic quantum field theory approaches to holography, which are basically orthogonal to these approaches that by Strominger. So later in this talk, I'll basically be commenting on these decoherence effects and basically these holographic proposals. Okay, so all of these ideas and these citations that I gave you before are quite old, and these have been resurging in the literature and in the current research mainly due to the ideas presented by Strominger. And so Strominger, this is his infrared triangle, and if you're the vertices of this infrared triangle, I think personally, are interesting on their own right. They don't necessarily need to be connected in this way, but the edges of this triangle are meant to evoke a kind of equivalence between these three ideas. And if you're interested in the validity of this triangle in all space-time dimensions, including 4, then I'd point you back to my original paper here. So in this talk, we will be looking at 4 space-time dimensions, and we'll be really just discussing with quantum gravity within the range of the validity of this triangle. So we'll see what these edges really mean in this particular context. Okay. So just as a kind of roadmap for this talk, I'll first be discussing, classical gravity. We'll have to basically collect some ideas of what do we mean by classical radiation, these underlying symmetries, and the memory effect. And the eye towards all of this is to really understand the implications of these results in the quantum theory. So in particular, we'll see that these infrared divergences and the memory will correspond to these infrared sectors, and we'll really have to we'll have to see how to put these infrared sectors together in a consistent way to construct a Hilbert space structure or infrared finite S matrix. And finally, we'll see there is the constraints that we derive on this Hilbert space structure will correspond very nicely to what's so-called the dressing in QED, and we'll see what the corresponding constraints imply for quantum gravity. Okay, so let's first jump into classical gravity. I should also say, just feel free to interrupt me at any point if you have any questions. I will be pausing at certain points in the talk just to field questions as well. So before we transition. So what do we mean, or what is the kind of setting of these or a class of spacetimes I'll be considering are asymptotically flat spacetimes, which are characterized by admitting this kind of null boundary here. So a null boundary is denoted by Scri, which has a topology of R across the 2-sphere, and these coordinates that I'll basically be using ubiquitously throughout this talk are the so-called Bondi coordinates. So you can coordinatize this spacetime in the following way. So if you flash a light bulb, then the imprint of this flash of the light bulb on this null boundary here is is topologically a 2-sphere with this metric Q, which is the metric of the 2-sphere. And we coordinatize the null geodesics emanating from this light bulb in terms of this parameter R, which is the you can think of the luminosity or the distance. It's referred to sometimes as the luminosity distance, but basically there's no relation to the cosmology at all. It's just the statement of you're coordinatizing this null geodesics emanating from this bulb. And then finally, this retarded time coordinate here runs up and down this cone here. So this is the R, and then the two spheres. These are these cross sections. So, and we demand, well, this metric is asymptotically flat. Is if I move off in these null directions, the metric asymptotes to a flat metric, plus in these coordinates order 1 over R, corrections to this asymptotic behavior. Okay, and so if we're expanding the metric, so we need to basically understand, in order to quantize the classical radiation, we need to first understand this, where does this radiation come from? So if we're expanding the metric in powers of 1 over R near null infinity, the classical radiation is really encoded in this order 1 over R piece. And how does that work? Well, you can basically, you project the order 1 over R part of the metric into the asymptotic sphere, and you remove its trace. So this is known as the shear at Scry, and you can basically think of this, roughly speaking, as the waveform. If you're thinking of a LIGO detector of some sort, this is roughly speaking what you would be referring to as the waveform at Scry. And the gauge invariant degrees of freedom are encoded in what's known as the Bondi-News tensor. So that's the time derivative of this asymptotic shear. Okay, good. So this is the gauge invariant degrees of freedom, and I mean, with an eye towards the quantum theory, you can straightforward to get the Poisson bracket structure, which is if you take the Poisson bracket of a news with another news tensor, then the Poisson brackets are it's a delta function in the angles along Scry, and it's a derivative of a delta function along retarded time. And the metric, the combination of metrics here is just ensuring that you have, the Poisson bracket is trace-free separately on each of these pairs of indices.
Just to be clear, n prime is not the derivative of n?
Yes, to be very clear, yes, that is correct. I had to denote a completely different news tensor than n, but yeah, that's a very good point. It's not a derivative.
Not a derivative.
Yeah. Okay, so given this, classical radiation, one can something that we're definitely going to need for the rest of this talk is the asymptotic symmetry group of asymptotically flat spacetime. So roughly speaking, the asymptotic symmetry group is the group of diffeomorphisms that preserve my boundary conditions. There are these so-called Bondi coordinates at Scry, and surprisingly, the structure of the asymptotic symmetry group was found to be, well, not the Poincar group, but the so-called BMS group, this infinite dimensional BMS group. So basically, for the rest of this slide, I'll just be explaining what I mean by this BMS group in a little bit more detail. So the Lorenz transformations are this group L here. Well, they act as conformal transformations on these asymptotic spheres. So these conformal transformations are these, omega squared here. And so this is really not the kind of new detail. The new parts of this BMS group that make it different than the Poincar group are these so-called infinite dimensional set of super translations. And the super translations basically correspond to these angle-dependent time translations at null infinity. And so to give you basically a little bit of handle of what's going on, so effectively each spherical harmonic is a super translation, and each spherical harmonic generates an associated super translation charge. And so the L equals 0 charge is that corresponds to basically a time translation. And the L equals 1 charge, and therefore the charge is the mass, and the L equals 1 charge, well, that's a YLM, that's a L equals 1 has a degeneracy of 3, and that generates the 3 independent momenta of the space-time. So the higher super translation charges, the higher harmonics of those have no analog in the Poincar group, and they really are new charges and new symmetries that arise from the BMS group. So, And something that I'll basically be using throughout the talk is that, so you basically get a number, that's what these charges are. You get a number for every spherical harmonic. So you effectively you can represent the full set of super translation charges as a full functions of angles, worth of information on a cut of scry. So you're basically, you can encode each number of the spherical harmonic all together, package it into one functions of angle. And this is, so I'm not going to give you the formula for how to compute this thing. I'll just give you, it's really not so illuminating. I'll basically, in every situation we'll need this charge, I'll give you the precise formula for the situation that I have in mind. But if you see this charge at all in the future, I'm referring to the super translation charges. Okay, and so the picture I want you to have when you're thinking about the super translations are that it's an angle-dependent time translation. So if I start with an initial cut of scry and I apply a super translation, then I end up with this kind of wiggly cut at late times, depending on where I am on the sphere. I move forward in time by a different amount. Okay, and so the last thing we'll need before we turn to the quantum theory is, the so-called memory effect. So the memory effect is the permanent relative separation of some array of test particles, so idealized LIGO detector, that's, freely floating at null infinity, brought about by the passage of some burst of gravitational radiation. So how do we encode this effect? Well, it's encoded, geometrically in terms of a memory tensor. So this is a tensor on the two-sphere, which maps my initial displacements of my test particles to a change in the final displacements of my particles. So that's what this memory tensor is doing. And you can basically visualize this effect in the following way. So if you have some initial relative separation of my test particles, and I geodesically transport these particles, forward in time, on scry, what you'll see is that due to the passage of this burst of gravitational radiation, the test particles will suffer a permanent displacement. And I basically depicted it here. This should look very familiar to you. Basically, the map is precisely the map of a super translation. So that's the connection between the memory and the super translations. You can basically write the memory effect precisely in terms of these super translation functions. It's effectively a potential for these memory effects. You take two derivatives on the asymptotic sphere to produce this the memory tensor. Okay, and so what we'll need, basically, the last two classical ingredients we'll need are basically the two equivalent formulas for the memory effect. So one is entirely in terms of the radiative data, and it basically is that the memory is completely determined by the early and late time asymptotic shear. So if you're thinking of the gravitational waveform, if the gravitational waveform, doesn't settle down to its original value at early to late times, then you have a non-vanishing memory effect. So I should note that the shear itself is a gauge-dependent quantity, but the difference of the shears between early and late times is not. It's a gauge invariant quantity. Okay, and the other formulation we'll need is in terms of super translation charges. So if you can write the memory effect, well, two derivatives of the memory effect on the sphere precisely in terms of the difference of super translation charges between future time like infinity and spatial infinity. So these are the charges that you compute at asymptotically future times and then at asymptotically space-like directions, and then you also get a contribution due to the total flux of radiation energy to infinity. So just to again give you just a picture, because these are kind of the core foundations of this talk. So if you are, for example, considering, I've drawn here the conformal diagram of some black hole merger. So this is a conformal diagram, so you shouldn't trust you shouldn't trust distances at all. You can only trust angles. So in particular, these at early times, the black holes are very widely separated from each other, but they just look like they're close because they're squashed together by the conformal factor. So if I have some two incoming momenta of my black holes, and they merge at some, later time, and I've basically, so they're emitting radiation the entire time, but they, emit some huge burst of radiation at the event of the merger, and they coalesce to form some final black hole, this given by this outgoing momenta, then this merger will generically produce a non-vanishing memory effect. And so if you're looking at the shear, you'll see at low frequencies, you'll basically see this step function-like behavior between early and late times. And that's a signal that you have a non-vanishing memory effect. And additionally, you could, given this space-time, you can compute the charges at spatial infinity and the charge at future time-like infinity. So the charge at spatial infinity will depend on just the incoming momenta. The charge at future time-like infinity just depends on the outgoing momenta, and their difference will basically contribute to the memory effect, as well as the total flux of radiation energy that makes it out to null infinity. Okay. Yeah.
Can I just stop you for a second? When you were describing the memory effect, you talked about particles at null infinity.
Yeah.
Now, of course, particles, test particles, time-like particles, don't go to null infinity. And the only particles at null infinity would be null. And that's not really what you have in mind, I think, right?
Certainly not.
Okay, so we're talking about particles at some large radius.
Yeah.
And some relative. Yeah. But what I just wanted to clarify is, if you think about test particles at large radius with some separation, the wave goes by, you get some different separation.
Yeah.
To describe that in terms of null infinity, what are you doing? Are you taking the particles at finite radius and shooting outgoing null geodesics from them to get corresponding trajectories on null infinity, or how do you map?
So to look at it as a map on null infinity itself.
Right. Yeah. The description in terms of null infinity that you gave is not the way I usually think about a memory effect. And I think so. I usually think about it as particles at some large but finite R.
So I guess so this it's a large but finite R, and they're so I think I completely agree with you that the test particles will, it's perfectly consistent to think about it in that way. That I think the key point is that this map here is basically you're looking at the relative displacements at leading order in 1 over R. So you are not necessarily at scry, and so this picture is a little misleading in that way, because it's kind of showing you a map on scry, but you're kind of pulling back the geodesic deviation to scry, and by taking the order 1 over R part of the geodesic deviation, and the map on the geodesic deviation can be thought of as a map on scry. But you're right that the particles themselves are moving at order 1 over R, so they're moving at some finite distance away from scry.
I see.
Define this as some limiting procedure, presumably where you have your particles, massive particles following time-like trajectories, which are almost out at scry. If they're very large radius, they're almost following scry.
That's right, and you're basically pushing them as far out as you can go, or you want to go, or whatever. But the what I'm drawing here is basically the pullback of the deviation vector on that you would get that is non-vanishing at order 1 over R. So the change in the deviation vector is what's not vanishing at order 1 over R, and that's what I'm drawing at scry. That's a completely well-defined vector on scry. But the particles themselves, I agree that I should you shouldn't really think of these as particles. You should probably the better way of thinking about it is, what is the change in the deviation vector, as you were kind of.
Okay, I got the picture now. So this is really representing the limit as the particles are moving out towards scry along some outgoing.
That's right.
Thing, and how they change. Yeah, thank you.
Good. Okay, so well, this was a point where I was going to pause and ask for questions anyway. So if anyone has any other questions to ask, we could take them now, or again, you can interrupt me whenever. Okay, so now let's just turn to the quantum theory. Well, we'll see the implications of, well, the memory effect and these symmetries on the quantum theory of gravity. Well, so the first question you should ask is, what quantum theory of gravity am I thinking about? Well, it was, it's basically, it's shown by, well, I think I have the citation here. Yeah, the citation in the next bullet point is that by Abe Ashtekar, that you can really define the kinematic structure of the theory, the in and out states, without in asymptotically flat spacetimes, without referring to the so-called bulk quantum theory, so quantum theory of gravity. So you can discuss, for example, what you mean by asymptotic states as an example, without referring to loop quantum gravity or string theory. And so the idea here is that on Scry, we're going to promote this news tensor here to an operator. So you now denoted with the hat, and what you do is you smear, well, this news operator gets smeared now with a test tensor, which these test tensors are trace-free test tensors on Scry with very fast fall off in retarded time. So this basically renders these this operator well defined. So these integrals are now well defined, and you can then define the algebra of observables at Scry by promoting the Poisson bracket algebra that I showed you earlier to now a commutation relation between news operators. So you take a news operator, and its commutation with another is given precisely by this Poisson bracket that I gave you earlier, up to a factor of I, and you smear in with these test tensors that to make these integrals well defined. Okay. So this defines for what I mean by the in algebra or the out algebra, and you can do this for the in algebra as well. And then you can basically ask, like, is there a natural Fock space structure at Scry plus? And you can ask the same question at Scry minus, corresponding to a unique BMS invariant vacuum state. So the existence of such a vacuum state has been shown by, well, it was first shown by Kay and Wald on killing horizons, but it's very easy to adapt this proof to null infinity, which was done by Dapiaggi in 2017. So there exists a unique BMS invariant vacuum state, and you can define this Fock space structure by a one particle norm on this Hilbert space, on this Fock space. So the one particle norm is given here. So if I take my test tensor, which is given by this S here, and Fourier transform it and square it, then you integrate with respect to frequency space with this factor of omega, and you integrate over the asymptotic sphere, where this is the measure on the asymptotic sphere. So if this is basically equivalent to the Klein-Gordon inner product or Klein-Gordon norm that you would have guessed for the for a scalar field, the symplectic product of for the scalar field, but now you're replacing the function for a test function for a test tensor. Okay, and so the key point is that, or the question is, well, if I start with an element of this, of this Fock space, and I, do some scattering type, experiment, then does the outstate also, end up in this, this natural Fock space structure? And so of course, the answer will be, there's more to this talk. So the answer is no, but let's, and the reason why is because of the memory effect. So the memory effect is, the way to understand this is to basically, let's try to construct a solution with memory out of these, out of this BMS invariant vacuum. So the memory is a generic property of the out field. So I can basically take a, a representative solution, let's take this sigma AB, and formally construct a state with memory by taking my BMS invariant vacuum and then peaking it at some classical solution with memory. So this is a coherent state peaked at the classical solution. And the picture you could have is the following. So if I wanted to just approximate what this classical merger situation was doing, but in the quantum theory, you could think about the state. I mean, the in state is effectively the unique BMS invariant vacuum state, and the out state is is very well approximated by a coherent state peaked at this classical solution for this classical merger process that I showed you here. And importantly, the classical solution with memory will have this kind of step function-like behavior from early to late time. So that's going to be important. So the reason this is a formal construction is because this state defines an element of the usual Fock space if and only if it has finite norm, in that it contains a finite number of particles. But the key point is that if you have, if this classical solution has a memory effect, then the Fourier transform will diverge like the Fourier transform of a step function, like 1 over the frequency. And therefore, the norm of the outstate will be logarithmically divergent at low frequencies. And this is the origin of all, infrared divergences, well, in quantum gravity, as we see, but also in quantum field theory, is that basically that the state itself has a non-vanishing memory for the outstate. Okay, so this is not, a problem. The psi defines an element of a different Fock space, this F delta here. However, if the memory is non-vanishing, this F delta is unitarily inequivalent to the usual out Fock space. And so for this classical process, you really need to include this F delta here. But however, if we, sorry about that typo. So if we include quantum matter into the game, then you'll have non-vanishing amplitudes for various different out memories, and therefore we need to include all of these memory Fock spaces for all uncountably infinite memory. So this is the infrared problem, basically, that when you do quantum theory, you really need to incorporate all of these uncountably infinite set of memories. And basically the main point of the rest of this talk is how should we do this in a consistent manner that is preserved under scattering. And let me just say that these infrared divergences that we have in quantum gravity have direct analogs to the infrared divergences that we get in quantum field theory, or sorry, in quantum field theory and in QED, for example, which corresponds to the electromagnetic memory effect. And the standard approach to dealing with this effect is to simply choose an infrared cutoff and integrate out all the low frequency radiation. However, I hope now it's clear that this procedure necessarily removes the memory effect from the set of observables. And furthermore, it really doesn't deal with the fact that if your aim is to have an infrared finite S matrix description of the scattering, then you really need to be including these states with memory. Okay, so at this point, I think let me just also pause again, because before we move on and really try to construct these Hilbert spaces, if there's any questions. Okay, so the general question here is, well, is there a Hilbert space construction which includes all of these uncountably many memory Fock spaces?
Maybe just a quick question.
Yeah, go ahead.
Remind me, is it true that there is a naturally defined vacuum initially, or isn't it the case that this is telling you need to consider all the different vacua with all of the soft charges?
No, so there is a unique BMS invariant vacuum. All of these other, I think they're referring to these displaced vacua, these other vacua that are not, well, they basically are not BMS invariant, as we'll see. So these other ones are basically, the unique BMS invariant one is the one with no memory. And all the other ones with memory are not BMS invariant. And that's the real problem, to incorporate this into a BMS, a Hilbert space that implements the BMS group is one of the key problems we'll be addressing in this talk.
Yeah, okay, so you have to include all of them in the end, but there's a natural choice of a zero, so to speak. Yeah,
there's a natural choice of a zero, but the problem is you're not even preserved in the zero, right? Like, so the outstate will generically be some, combination or of states in all of these memory Fock spaces. Yeah.
Right.
Okay, good. Okay, so let's just try a bad example before we do a good example, or try to figure out what's going on here. So one could, for example, consider an uncountable direct sum over all of these memory Fock spaces. However, as hopefully it's clear that this uncountable direct sum is a non-separable space. It doesn't admit a countable basis. It's an absolutely gigantic space, and there's really no guarantee that this space is preserved under scattering. So if I start with an element of this space, it's not clear that the outstate is also going to be an element of this direct sum space. So to put some guardrails on this problem, so we're not allowed to consider pathological Hilbert spaces. So we're going to seek a Hilbert space for scattering, which is one, separable, it admits a countable basis, and two, unitarily implements the Bms group. So the Bms group act as unitary operators on this Hilbert space. Okay, so the idea is that these separately are going to constrain the space of Hilbert spaces, the set of possible Hilbert spaces for quantum gravity and in quantum field theory. Okay, so the idea is that, first, the separability implies that the Hilbert space cannot be a direct sum over all of these, memory Fock spaces, but rather it actually must be a direct integral. So that'll be basically explaining what the, at least in words, what a direct integral is for this slide. And so a direct integral, this is the symbol that's used, and you're basically kind of stitching together these memory Fock spaces with some choice of infinite dimensional measure on the memory space. So the technical word that this is a probability measure in the sense that it's, its integral over the memory space is 1. And so you basically have to choose this measure, and a state in this Hilbert space is basically has a distribution in memory now, as opposed to the direct sum where you had states with definite memory. This is now allowing for states with distributions in memory, and a state is in the Hilbert space if its square integral is in this direct integral space is finite. And just to make sure that it's not just a mathematical artifact to you, the choice of direct integral or measure can be really thought of as a choice of entanglement between the soft degrees of freedom. Basically, as opposed to the direct sum picture where you're allowed states with definite memory and states with different memory are orthogonal to each other. So the states now with different memories or different distributions of memory can now have a non-vanishing inner product with each other. So that's the general idea with this measure here, is that you're prescribing a choice of entanglement. Okay, so now, yeah.
Sorry for interrupting. I'm just trying to understand. So, you have these different sectors labeled by memory, but it presumably doesn't make sense to say, keep the state fixed and just change the memory a little bit, right? You don't have a natural way of identifying, quote, the same state in the sectors with different memory.
You don't have a natural way of identifying. Sorry, I'm not sure I understand your question.
Well, if you go back one slide,
sure.
You're doing some integral over the memory of some state. That psi sub delta is a state labeled by memory.
Yes, that's right.
Is that just a choice of state in each of the sectors labeled by memory?
That is a choice of the state in each of the sectors labeled by memory. That's right.
Okay.
So you basically are allowed to choose in every F delta a state, and then you kind of have to integrate over the memory, that spans all of these choices of different states.
I see.
I think, Gary, what you're asking is, if I give you the state in one memory, you naturally find another state, sort of in quotes, the same state in some other memory. And
yes, I thought that's what was being assumed, and I was going to question that. It didn't seem.
No, so there is no natural way of identifying states between different memories. So I think Gautam is allowing for completely random choices in each memory sector.
Yeah, I'm allowing for there is no way to identify these in, you know, if you, well, yeah,
Right.
I will basically assert, and I am agreeing with Kartik, that there is no way to identify these memory Fock spaces together in a canonical way. So you really are allowed to the freedom of choosing individually in this direct integral, you know, a state in every of these, every element of this Fock, or every one of these Fock spaces.
Okay.
Okay. So now we're basically, we'll understand the, we want to understand the implementation of the BMS group. So we'll do this in two steps. We'll first consider the super translations. And the super translations, well, they don't change the memory of the state at all. However, their implementation implies a smoothness condition on the memory. So how does that work? Well, you pick a state, this psi delta here, let's say, with which is an element of this, Fock space F delta, and recall that it is defined relative to a memory representative, this sigma AB here. If I time translate the state, well, the time translation of the state lives in a potentially, different Fock space, this F delta, this tau or T of F delta here, with memory representative given by the time translation of these of the sigma here, this memory representative. And by the same reasoning as before, the Fock space F delta is unitarily equivalent to this T of F delta that I got from this memory, the time translate of the state, if and only if the difference of the, the representative and its time translate has a finite one particle norm. Okay, so this seems kind of innocuous because the shear minus its time translate has zero memory. So therefore, the frequency integral is totally okay. However, this implies that the angular behavior of my memories have to be, severely constrained. Well, in particular, they cannot be too badly behaved. They have to have a finite, it turns out, L2 integral on the over the sphere. So in general, I did this for the time translations, but you can prove this for the full super translation group. They are unitary if and only if the memory is sufficiently smooth. Okay, and so the Lorenz transformations, well, the Lorenz transformations change the memory of the state. So let's see how that works, and we'll see that this implementation actually constrains the measure. So the memory is basically, as I mentioned before, determined by a super translation function. And if under a conformal transformation, which is the Lorenz boosts, the super translation functions actually have conformal weight, +1. So they, I have a non-trivial action under the Lorenz boost, Lorenz transformations, and therefore the memory itself will, change under a Lorenz transformation. So the Lorenz boosts are maps between different memory sectors, and I mean the kind of intuitive picture I want to give you, without getting too into the weeds, is that of an infinite dimensional measure, the idea is that you're mapping between these different memory sectors, but you can reabsorb this map as a map on the measure if the measure is Lorenz invariant. So if the measure itself is Lorenz invariant, then the Lorenz transformations act as a unitary map on this on my direct integral space. Okay, so the ingredients for that we're going to require is that, well, the Hilbert space is a direct integral. The support of the measure is the space of memories such that it's sufficiently smooth such that this integral is finite. And finally, the measure is a Lorenz invariant. However, this is still not incredibly constraining in the sense that the space of Lorenz invariant, or the space of measures, is very large. But regardless, it's unclear whether or not there exists even a unique choice of infinite dimensional measure that satisfies these constraints. And the interesting thing is that in QED, there is actually a very natural prescription of reducing the space of memories to a finite dimensional space. And in the sense of when you go to a finite dimensional space, there is a unique Lorenz invariant measure that one can choose in addition, and we'll see that these memories on this finite dimensional space will be sufficiently smooth. So this is the so-called Faddeev Kulish dressing, and for the next couple slides, I'll basically be explaining that. So are there any questions at this point? Okay.
Gautam, sorry.
Go ahead.
Can you go to the previous slide? So just so I'm clear, like criteria 1 is the Hilbert space is actually separable, right?
Yeah.
And the second one comes from implementing translations or super translations, and the third one is sort of accounting also for Lorenz. So
yeah.
I mean, these are just consequences of requiring some separable Hilbert space, and that Bms group is actually unitary.
Yes. So yeah, that's right. But basically the point I'm laying out here, or the reason I'm laying this out, is these constraints have never been written down, and the point is that when you want to do this in quantum gravity, we're going to run into a problem of this description, and so we really need to deal with this full set of constraints. Yeah.
Great. Thanks.
Okay. Good. So in the next 5 minutes or so, let's just discuss the Faddeev Kulish dressing idea. So the main idea is that memory depends on the low frequency part of the field. So in this regime, the electrons are effectively classical. And so the idea is that let's include only those memories that correspond to the memory of a classical charged particle. So that's the main idea. And so classically, the electromagnetic memory has a very similar form to the one that I showed you for gravity. So electromagnetic memory is a vector on the asymptotic sphere. If I take its divergence, you can write it in terms of the difference of, instead of super translation charges, large gauge charges. So these lambdas here are gauge functions on that are not vanishing at scri. And so like, for example, the L equals 0 part of this charge is just the actual electric charge. And then the higher harmonics are these large gauge charges. And so for a classical charged particle with momentum p, the charge at future time like infinity is totally determined by this outgoing momentum. So the momentum of this particle completely determines the outgoing charge. Gamma here is just the usual Lorenz factor, and this denominator is just the usual boost factor that one gets, in these formulas. M is the mass of the charge, and E is the charge. Okay, and furthermore, in the quantum theory, the Q at the charge at spatial infinity is a super selection sector. So the way to think about this is that the electric charge, as an example, commutes with all local observables, and as a result, you cannot consider two states that of different electric charge. They cannot be superposed with each other. This is the generalization of that to these these large gauge charges. And this was first proven by or highlighted significantly in this paper by Buchholz here. And so the idea is that without loss of generality, if I'm building a Hilbert space, I can assume that I'm in one of these large gauge charges, super selection sectors. And that, therefore, the memory of a classical charged particle is completely determined by the outgoing momentum of the electron. So it's this P here, which spans a finite dimensional space. So that's the key idea of the Faddeev and Kulish approach.
Question there.
Yeah, go ahead.
Actually, if you could go back. So if I think about a classical particle, you're associating with that the boosted Coulomb field. But you could just as well add some classical radiation to that, and you could, in effect, change the soft charges is one way of putting it. You could have the classical particle together with some radiation that gives it some different field configuration that satisfies the constraints and has effectively different soft charges. So you're making a choice at this stage, I think.
You're making a choice at this stage. So the charge at spatial infinity, you can choose that in advance. So let's say I set it to be 0 as an example. So I want to work in the 0 super selection charge. then this equation determines, well, the momentum of the electron, the outgoing electron, determines the soft radiation precisely by this formula. And that's the key point. So when you work in a superselection sector, the outgoing momentum of the electron determines the soft radiation. The higher frequency radiation is not determined. So that you're allowed to add hard photons to the game, but that doesn't change the memory. That's the key point.
Yeah, I guess you could also add soft photons, but you would specify those by data on sort of scry minus or something.
So that would be changing your super selection sector, though. That would be effectively is what. So if you fix the super selection sector when you're in this construction, and then the memory is completely determined by this outgoing momentum.
Okay, thanks.
Okay, so the idea of Faddeev and Kulish dressing is to simply correlate, well, the plane wave of the electron to the electromagnetic state with memory corresponding to the memory of a classical charged particle. So you no longer can talk about an electron alone. An electron is now a composite object where you tensor in the electromagnetic field corresponding to the memory with memory that has the memory of this of the classical electron in this super selection sector. And so in any super selection sector, the one particle Hilbert space is still a direct integral space, but now it spans a finite dimensional space. So the measure is now the unique Lorenz invariant measure on the hyperboloid, and you're basically just tensoring so this is the one particle space is what I'm showing, is the tensor in the Dirac space of plane wave states, and you tensor in the electromagnetic field, this F deltas that I was showing here, but you're only allowing these F deltas that have these classical correlations. Okay, and then the n particle case is treated basically the same way. You consider an n particle Dirac plane wave state, and you tensor in the memory in a super selection sector associated to n outgoing charged particles. Okay, and one can basically just directly check that the memory that you get from these outgoing charged particles, as long as the super selection sectors you choose are sufficiently smooth, the memory itself satisfies these smoothness conditions. And the Hilbert space then implements the Bms group, and it's highly plausible. This is the best basically that one could do. You've satisfied all the criteria we wrote down, and so it is therefore highly plausible that the in states map to out states under scattering. And this was actually exactly proven by Froelich in the case of non-relativistic QED, and it's very plausible that this persists in full QED. Okay, so let's basically just go over what happens in gravity now. So you can try to implement basically the same ideas. So let's now write the same kind of relation for an outgoing body with this form momentum given here, and where the memory now is determined by, well, this is the charge that you get for this body at the future time-like infinity. This is the charge at spatial infinity, now the super translation charge at spatial infinity, and there's an extra contribution now due to the flux of gravitational radiation energy to infinity. And so I want to reinforce the point. So the Faddeev Kulish dressing in QED relies on the ability to independently specify the electromagnetic degrees of freedom and the electron degrees of freedom, right? So these both span their own individual Hilbert spaces, and you're basically tensoring them in some clever way by basically to construct a sub-Hilbert space of composite states which satisfy these classical correlations. Okay, so the reason I'm emphasizing that is that there's now no analog of this procedure in GR because of this, precisely this formula. So one cannot independently specify the source, which is now the field itself, which is these hard gravitons, from the field, right? The field, which is given, which lives in its own Hilbert space. One cannot tensor the field with itself to form a sub-Hilbert space to enforce some sort of correlations. Okay, So the key point is that gravity acts as its own, this is unique to gravity, it seems, that gravity acts as its own source of memory. And so the Faddeev Kulish construction fails, and memory is you cannot require that it spans a finite dimensional space, and it really just spans this full infinite dimensional space that I was referring to earlier.
So, Gautam, this only happens if you're doing, if you're doing linearized gravity.
Yes.
The new squared term doesn't come in, right?
Yeah, I completely forgot to mention that. Yeah, so in linearized gravity, one can do this full construction, right? The key point is that in linearized gravity, the nu squared, this flux of radiation energy, does not contribute to the memory at all. And so you have a clear separation of what you mean by source and field. But in nonlinear gravity, there is now no such clear separation, and therefore one cannot. Yeah, so thank you for bringing that up. That's a very key point.
And this doesn't even happen in Yang-Mills. So it's not that it's not that the equations of motion are nonlinear.
That's right. Yeah, so in Yang-Mills, you do not get a flux of nonlinear, contributions to anything, but in the gravitational case, you do. So this is a unique to the quantum gravity case. Okay. So in the last 5 minutes or so of this talk, I'll basically just quickly page through another alternative way of doing things, just to reinforce the final point I'll be making, which is that, so we have this large class of possible infinite dimensional measures, but within those class, it's a priori unclear that there exists a single infinite dimensional measure that will satisfy our constraints. That was not the case in the finite dimensional case. Finite dimensional space of memories, where you can just simply write down a measure that satisfies all of our constraints. And so let's just explore this in the case of Gaussian measures. So I don't have time to get through the construction of an infinite dimensional Gaussian measure, but the key point is that it's uniquely determined by some choice of inner product on the space of memories. And so the key idea is that if you want a Lorenz invariant Gaussian measure, you need to find a Lorenz invariant inner product on memories. And one can prove that there exists a unique Lorenz invariant inner product on memories, which is simply this L2 integral that I was showing you before in the completely different context. So this integral here is a Lorenz invariant, and you can use this to construct a Gaussian measure. And the key point is that we prove that the space of memories with finite norm, this finite norm induced by this inner product, are actually a set of measures 0 on the space with respect to this Lorenz invariant Gaussian measure that you can construct here. Another way of basically saying the same thing, a direct integral construction constructed from a unique Lorenz invariant Gaussian measure, has the space of memories in which you can implement the super translations are a set of measure 0, and therefore they fail to implement the super translations. And since I'm speaking to people who probably are familiar with path integrals, you actually encounter this in path integrals as well. So let me just quickly say what that is. Well, the space in a path integral, you're basically constructing a Gaussian measure with some action S. The action is effectively your inner product. And it is the case that in the path integral that the space of finite action states or fields have 0 measure with respect to this with the Gaussian measure that you construct with respect to this action. That doesn't mean that these these kind of saddle point approximations that people make are not valid. You can actually prove that they're very, the measure is tightly, supported around these finite action solutions. And there's actually a rigorous way of, doing this whole thing. But in this Hilbert space construction, we really care about the support of the measure. We really need the measure to be have support on the space of memories that have finite inner product, and that's just simply not the case in the case of this Lorenz invariant Gaussian measure. Okay, so I'll simply summarize. I was going to also talk about some of the holographic ideas, and if anyone has any questions about that, I'd be happy to. I guess I have some backup slides now, but I'll simply just summarize where I am since I'm running close to the end of my time. So these infrared divergences are a physical effect, and if one wants to incorporate them into to construct an infrared finite S matrix, we've basically provided the ingredients that one needs. However, it seems that even with these ingredients, there doesn't appear to be a preferred Hilbert space structure for quantum gravity in contrast to the QED case. And so if you want to consider things like scattering between in and out states, decoherence due to soft radiation, and holography, it seems much more satisfactory to work in the algebraic formulation of the theory, where one does not need to a priori specify a Hilbert space. However, this needs a significant improvement on the current formulations of the S matrix in the sense that one needs to formulate an S matrix on algebraic states. So this, I think I'll just end here and take any further questions since I'm running short on time. Thank you.
Thanks, Gautam, for a great talk. I know we had a lot of questions during the talk, but I guess we have time for one or two more. Does anyone have any other questions?
I guess I do. I mean, if I remember correctly, when Abhay was, developing this asymptotic quantization, he talked about super selection sectors associated with these different memories, I guess. And I think Andy may have also been talking about super selection sectors in quantum gravity. So you're saying that that's not right? That's not feasible because you scatter from one to another or something?
Yeah, so the idea of a super selection sector, maybe, so I'm not sure about the terminology that Abhay used, but or if he was referring to exactly these memory foxes, but yeah, it's generically true, and I believe it's certainly something he pointed out in his own monograph as well, is that you scatter between these memory fox spaces. So there's, in that sense, it's not a super selection sector. The super selection sectors are kind of, they're conserved charges of the theory, and they and also, they dissatisfy other constraints as well. So I think that that's not what I would advocate, and I think that I'm not sure if what terminology that Abhay was using when he was referring to that, the super selection sectors.
Any other questions? Well, if not, let's thank Gautam again.
Yeah.
Thanks.
Thanks.